that concludes that presentation from Dan. All right, everyone can see this. Hopefully next up is our speaker, Alex Byrley. Dr. Alex Byrley is a research scientist with Mastodon Design in Rochester, New York. His role focuses on designing and prototyping signal processing and machine learning algorithms for wireless radio frequency receivers. He received his PhD in electrical engineering from the University of Buffalo in 2020. His research is focused on joint radar communications waveform design and electronic intelligence. So I'll pass the torch to you, Alex. Oh, you're muted.
Okay, thank you very much, Nick.
All right, yeah, you're welcome.
So let's see, let me share my stuff here.
All right. Yeah, it's displaying correctly. We can see it.
Okay, great.
All right. Take the floor then.
Perfect. So welcome to my talk, everybody. My name is Dr. Alex Byrley. I'm a research scientist with Mastodon Design in Rochester, New York. Today I'm going to be talking about a new kind of waveform that I've been developing with Dr. Adley Pham over at UB. We're calling them logarithmic frequency chirps. So before I start, I'd like to thank Zheng Yu for inviting me today and Nick for moderating this session. I've been looking forward to giving this talk as I've got my PhD from UP. So, yeah. So today I'm going to explain these waveforms, with an example. Then I'm going to talk about the main parts of the receiver, which are the fractional Fourier transform and the logarithmic frequency transform. Then I'm going to illustrate the main processing flow with an example. We will wrap up with some suggestions for applications wherein these waveforms are well suited, and then we'll talk about plans for future work. So this is going to be a rather high-level talk. I'm going to leave out some details for the sake of time. I mean, mostly actually it's just a lot of boring math, so you're not missing much. But I hope that you get the main ideas. More details are coming in a peer-reviewed journal paper next year, so watch out for that if you're curious. So getting right down to brass tacks here, logarithmic frequency chirps are a new class of joint radar and communication waveforms that are built by mapping what we call a good code onto a logarithmic frequency axis. The word good means that their autocorrelation has a high main lobe to side lobe ratio. So practically, this means that our waveforms can be detected easily if we have a matched filter. So we use the frequencies on the other end of this mapping as the center frequencies of linear chirp waveforms or linear frequency modulated waveforms, which we transmit wirelessly. So our design results in waveforms that are Doppler tolerant and Doppler estimation capable. They have good spectral autocorrelation properties, and they are low peak power and resistant to spectral jamming. So the Doppler properties all come from the simple fact illustrated here in the bottom left-hand corner, namely that the logarithm converts multiplication into addition, and this allows us to view the Doppler shift as a simple translation of a code that we build over the logarithmic frequency axis. So if we perform match filtering in the logarithmic frequency domain, all that happens is the response gets shifted in frequency. And the value of the shift then tells us what the Doppler shift is. So we can see this in the figure on the right? The difference in the location of the two responses, which are both good, according to our definition, by the way, is related to the Doppler shift. So here's an example of one of these waveforms. So the mapping that generates the frequencies is given in the top here. The code defines the mapping in the way that it tells us how to choose these a sub n values. The top figure shows that these chirps have overlapped support in frequency. So it turns out that we can overlap chirps like this to generate the signal in the bottom figure and still get these good spectral autocorrelation and Doppler estimation properties that we want. And we'll explain that in the next slide. So we see, if we take a look at that signal, I mean, it looks pretty nice, right? The peak to average power ratio, for instance, isn't too crazy. So, I mean, you can't just smash chirps together like, and get a signal like this. And you have to design it, right? And that's how all these parameters that you see here, that's how we do this. And I'm not going to, get into the exact design procedure today. That's going to show up in the journal paper, hopefully. But I am going to convey the main ideas about what these waveforms can do and how you might build a receiver for them. So the key tool that makes all this work is the fractional Fourier transform. So we use the fractional Fourier transform to take a chirp and basically turn it into a sinusoid. In other words, we take the extended spectral support of a chirp and map it to an impulse. So on the left-hand side, you can see, let's see, I can use my laser pointer. Yes. So on the left-hand side, we have the time and radial frequency plane here. We can see that this line is representing a signal with a linearly increasing frequency over time. So we see that it's at an angle alpha with the y frequency axis. So the fractional Fourier transform rotates the time frequency plane through this angle to arrive at the right-hand picture. A signal with constant frequency over time. In other words, right, a sinusoid in the U domain. So the video here shows what happens to the amplitude spectrum as we rotate in the plane. So we see that the chirp, right, is approaching a delta function. So, and we want to notice that also the amplitude is increasing as well, right, because the energy has to go somewhere, right? So as the spectral support gets smaller, the amplitude increases. And you can imagine, right, how this might be helpful in the presence of noise. So it turns out we can actually use this to detect chirps and detect our code as well. So on the top left here, we have an example of a multi-chirp waveform where each chirp is color-coded. Of course, the actual spectrum, the transmitted waveform, is a superposition, so it looks a little different, right? But I want to show you how the transform works here. So, remember that, but the fractional Fourier transform is a linear operator, right? So it works on each one of these chirps individually, like via the superposition principle. So after we apply the fractional Fourier transform, we're going to get this figure on the top right here. And we can see that each chirp gets mapped into its own impulse function, right? 4 chirps on the left and 4 impulses on the right. So we map from linear frequency, right, C, to another variable. We're just calling U frequency here. And the relationship is given by this equation. And that's how we have to invert that, right, to get the summation with the delta function. So the trick to getting this to all to work is that the chirps are all at the same angle in the time frequency plane, right? And so they have all the same chirp rate. And so this allows us to define a match filter, like here on the bottom right. Right? We see that it's, the two figures here, the patterns are very similar. So if we apply it, right, we get this figure on the bottom left. We have this nice pattern that we want, the tall main lobe and the small side lobes. And the reason why this happens is because of the specific pattern by which these impulses get spaced after the fractional Fourier transform. So now that we know how we can detect chirps, we need to know how to modify things when we have a Doppler shift, right? To do that, we really need to understand what a Doppler shift is. So in radar and communications, right, anywhere that deals with electromagnetic waves, the Doppler shift is usually thought of as a linear shift in frequency, but this really isn't exactly right. It's the equation on the right-hand side here. We only get away with this, right, because the Doppler shift is so large that we can practically think of it like that. In reality, though, we need to think relativistically, right? So for instance, if the target is moving towards you, towards your receiver, what you're going to get is a waveform that's compressed in time, right? And therefore it appears to be higher frequency, right? The opposite is true when it's sort of moving away from you. So in other words, right, we can model the Doppler shift as a time scaling. And if we do this, when our transceived waveform is a linear chirp, well, we get another linear chirp with a new chirp rate and a new starting frequency. So as you can see, we have you can imagine that there might be two ways to estimate the Doppler shift, right? The first way is to sort of adjust the fractional Fourier transform angle until you sort of get that really large peak that you want. But this is kind of time consuming, right? We have to run multiple transforms, check for the the maximum angle, etc. The easier thing to do, at least computationally, right, is to exploit the fact that the start frequency changes by a multiplicative factor, right? Now, since the entire waveform is getting compressed, the center frequencies are all going to change by that same factor, right? So this slide basically explains it, right? The chirp rate changes according to this formula because the formula in the last slide and here too, that because the whole signal gets compressed or expanded from the receiver's perspective. So yeah, so the center frequency gets multiplied by the Doppler shift as well. So if we warp the frequency axis after we apply the fractional Fourier transform, we can separate out the effects of the Doppler shift and the transform. Indeed, these delta functions are going to be uniformly spaced, or at least spaced, according to this A of n function. So we can do match filtering. And we know the reference frequency and the angle by which we took the fractional Fourier transform, so we can estimate the Doppler shift by match filtering the spectrum and finding the location of the peak. The exact equation is here. So now, when the Doppler shift is small, the angle that we take the fractional Fourier transform, it won't be too far off from the optimal angle, and we're still going to get these nice impulses. But, for instance, in radar, this is usually what's going to happen. But when the Doppler shift gets larger, relativistically, right, we're not going to get an impulse because our angle is going to be really wrong. So we need to shape the chirp spectrum such that the maximum will be at the center frequency. Right, this can be done by windowing, right? So we really have no problem with larger Doppler shifts either. So now we're going to show exactly how to do this. So step one, transmit your waveform, right? So here, Cn, if we want to use a Goulam 4, we're going to let delta C be constant and select An from this set here. C sub n could be nominally 1, but if we let it have a phase, right, we can use it to transmit messages. So step one, after all the processing, right, that you need to get the analog waveform into something digital, which we can even compute a fractional Fourier transform, we compute the amplitude of the received signal's fractional Fourier transform, right? And it looks like this. Next, we're going to logarithmically warp the frequency axis. Next, we're going to take the Z transform, right? Luckily for us, the Z transform of a pulse train is yet another pulse train. But the key here is that we get to take out all these terms, right? Because they're going to be constant. And the next thing we're going to do is initialize a match filter. You see, this match filter has this nice same form of the thing that's in the parentheses. And this is what's going to give us this nice pattern. So we're going to take their cross correlation, right? And you see that what's going to happen is the received waveform is just going to be delayed relative to the transmit waveform. Picture there. And then we estimate the Doppler shift, like that. So, yeah, I know there was a whirlwind tour, and I left out a lot to convey the main ideas succinctly. But I just want to summarize quickly. So, we've developed a new class of joint radar communication waveforms that we build by mapping a code onto a set of logarithmically warped frequencies, right? These frequencies we use as the center frequencies of chirp waveforms to transmit wirelessly. That gives us the following properties. Doppler tolerant and Doppler estimation capable, right? Because the match filter we define over the logarithmic frequency axis, and we saw how the logarithm converts a multiplicative change into an additive change, and that just shifts the response. They have good spectral autocorrelation properties because how we choose where these frequencies are spaced, or for instance, what the phase of the frequencies might be. They have low peak power and the resistance to spectral jamming because, of course, we use chirps, right? So we can take that energy we want and we can spread it over frequency. And resistance to spectral jamming, of course, because they're chirps. So here's kind of the high level of the receiver structure, right? And after we estimate the Doppler shift, we can do all sorts of other things, like for instance, maybe look in the time domain, right, to get a better idea of where it is exactly by adjusting a time domain matched filter. And the Doppler estimation equation is given here. So generally, these waveforms are really low probability of intercept, and they're, if you use them as a tracking waveform, right, because they can estimate a target's velocity from the Doppler shift from a single return, right? You don't need to send multiple pulses, right? And they simultaneously they have low peak power, right, by virtue of using the chirp. So these waveforms are particularly well suited for tracking dangerous objects like this guided missile destroyer up here, or fast-moving objects, right, like these hypersonic missiles here, without being detected, right, by an electronic intelligence system, because we can do things like hide in the noise, we can overlap chirps, we can, because these things can estimate Doppler shifts that are very large, we can move our platform. So when you use these things to their fullest capability, they will make a quite formidable wave. So future work is we're going to submit this to the IEEE transactions on aerospace. That's coming soon. And the next thing might be to look at what happens when targets are accelerating. Right? So when you accelerate a sinusoid from a receiver's, stationary receiver, for instance, we get kind of the same thing, right? We get something that looks like a linear chirp. And so it's not quite the same, but because the chirp rate is now dependent on how the sinusoid has started its original frequency. But it's similar enough that we might be able to do the same kind of things here. So here are my references. Yeah, so this work is basically an extension of my PhD work at Buffalo. So, well, thank you.
Yeah, great. Thank you very much. That's a very nice talk. And yeah, I'm glad to see that you're continuing to do that. I was on your dissertation committee, and you gave an excellent presentation then and did great work. So it's nice that you get to continue it.
Thank you.
If there are any questions from the audience, please feel free to punch them into the Q&A box. In the meantime, I could ask you if you can remind us again what the importance of using the fractional Fourier transform was in this case.
So let's see here, maybe I can show it here. Yeah, so the fractional Fourier transform, what that's going to do is get us these nice impulse response functions here. So instead of doing match filters with these chirp waveforms that are very extended, right? If we transform them to impulses first, the match filter, the response will look much nicer. And it won't be extended in frequency, and then because it's not extended, the Doppler shift will be much more accurate.
Oh, great. And then thank you. We have one question from the audience saying, we know that RF chirps are noise resistant. Are the log chirps even more noise resistant and jam resistant?
I don't think that they're any more noise resistant or jam resistant than a regular chirp. I mean, that's all it is, right? We're just using a linear chirp, right? All we're doing is we're spacing the frequencies in a pattern, right? Such that when we receive them, we use this pattern, for detection. So, the chirp itself is not really more resistant to noise or jamming, but it's what's coupled with the receiver, right? The receiver, and the fact that we're combining these chirps in this way gives us some extra signal to noise.
Yeah, great. Thank you. I know. So is this work also affiliated with the work you're doing at Mastodon?
No, this is just stuff I'm doing, volunteer with Dr. Fan.
Okay, great. All right, thank you very much. I don't see any more questions in the chat, so let's all thank the speaker again. And it was great to see you, and we'll go on to the next speaker. Thank you.
Great, thank you.